Good morning, everybody. Welcome back to class. I was planning to get Zoom going. If anybody's looking for the Zoom link, mostly you're probably not in the room if you were looking for it. Zoom's not going to be running today. I'm going to record this lecture some other way. Hopefully this way works and I can get this uploaded after class. But anyways, a couple updates for today. One thing I didn't mention last time that I probably should have highlighted, but I'll highlight it here today, is that iPads are indeed required to take exams in the class. Not quite sure why that's the case, but it is the case. But that does allow every one of you in the class to check out a university-owned iPad if you don't happen to own one. If you have one that's kind of old, I would just go check one out for the semester. You don't necessarily have to use it for anything else. You can if you wish, though. I think it's nice to have a stylus so you can take notes on some sort of device if you don't already have the ability to do that. But the only requirement for the iPad are taking the exams in the class. There's nothing else that you're going to be required to do with the iPad. So you really just need one come week 5 for that first midterm. I don't know if the department's going to let people not use an iPad, so I would try to make sure you acquire one of those iPads in the university at some point here in the next week or two. And so then the first required online homework assignment is due Monday morning before the start of lecture. Just be aware of that. There's a relatively small penalty if you do get it in late. So for some reason, you can't get the MyLab access set up over the weekend and you're into Monday morning doing this, it's like a 0.5% penalty per hour late. So I wouldn't overly stress if you run into some tech issues over the weekend, but there are some tech TA office hours. I think there's some for today. So if you haven't set up your MyLab and mastering access, check out the file. It's the start of term tasks link from our course homepage in Carmen. Just click on that. There's a setup file with a code in it. And then from there, there's a help file if you have issues. At the end of the help file, there are some office hours that are listed. So check those out if you need it. Okay. So let's get started here in chapter 1. So in chapter 1, we kind of have a brief introduction to chemistry. So we'll see some terminology introduced in the early half of chapter 1. And then as we get into the second half of chapter 1, we get into some sort of calculations that we'll do. So we'll talk about units, some dimensional analysis, and everybody's favorite topic that we were mentioning last time, significant figures. And so obviously the study of chemistry, I think we have all been introduced to the atoms as the building blocks of matter. So chemistry is the study of matter and the composition of matter. We talk about the properties of matter, the reactions matter can undergo is an important topic in chemistry, so some of the transformations that take place along with chemical reactions. We get an atomic and molecular perspective here in Chem 1210. So in chemistry, you usually like to try to think about what goes on from inside the atom. Now, for the most part, we can't really take a direct look at an atom. You can't really just take a microscope and zoom in on a single atom. But you can understand at the molecular level from other experiments that can be done. And so we try to get an atomic level perspective and use that to try to understand matter in a class like this. So as we proceed, it's really when we get into chapter 6, we start to think about the electron behavior, chapter 7, nuclear behaviors. We start to think about molecular structure, bonding, as we proceed in chapters 8 and 9. So I think chemistry is important to lots of different disciplines. I think that's why we have a room of 300 plus people, probably few or maybe even none of which are actually chemistry majors taking a chemistry class, as chemistry is important to lots of different disciplines. I think if you're going to be a doctor, I think it's good to know what types of drugs people are going to need to take just so you can understand the molecular drug interactions or have some level of understanding. Obviously, pharmacy is really needing of chemistry. Energy, different types of engineering disciplines, food chemistry, obviously come down to sort of understanding details at a molecular level. So some basic terminology that I think I would imagine this is mostly review, but it's really just kind of setting the stage for remembering and understanding what we mean by atom, what we mean by element versus molecule, etc. So an atom, I just think of a ball. So an atom is just one distinct, the simplest building block of matter is just one single atom, and then atoms can be comprised of different elements. So you can have like a hydrogen atom, a helium atom, a carbon atom. And when I think of these atoms, I'm just thinking almost like a beach ball, if you will. And there's like something within that atom that makes it specifically whatever element it is that it is representative of. And different elements have different properties. We're not going to go through all those properties here in chapter 1, but I think we can understand that hydrogen behaves differently than lithium. Lithium behaves differently than oxygen. Oxygen's different from carbon, et cetera. So atoms have different properties. You could probably remember, or sort of, you may have learn like those periodic trends and things like that. We come back to that in chapter 7, where that really gets into a big discussion of what really makes atoms different, why they have some of the properties that they have. So when we talk about atom, we're usually talking about a distinct, single building block, one single atom can be comprised of an element. Now, in terms of the elements, of course, I'm sure you've all seen the periodic table. We're not going to quiz you on the location of elements in the periodic table. You don't have to memorize hydrogen, helium, lithium, beryllium, etc. I would just make sure that you know, if we say the symbol, I want you to know the name of the element, and if we give you the name of the element, I want you to be able to look up the symbol if you need to look up like a atomic weight as you go in the class. But really not for any exotic element. A lot of times I don't even know the lanthanide and actinide series, the elements down below. Like I used to call, just when I messed up in class and a student once corrected me, and I was calling it the wrong element name for probably like 10 years, like praseodymium or something like that. So we're really talking about the first 4 to maybe like 5 rows of the periodic tables, the most common elements, the ones that we use in examples. I would just want you to know if I'm using copper in example, in an example in a problem, that you just know it's Cu. So you know which element to look up the atomic weight for should you need that. So it's just really name to symbol, symbol to name, kind of recognition for the first like 4 to 5 rows of the periodic table. Like the halogens are maybe a little bit more important. We use the whole row of the halogens in a lot of examples. The same thing with the alkali metals. We go through naming and understanding different groups of elements in like chapter 2. So we'll talk about some of the groups of elements and some of their properties a little bit later. But it's just kind of at now just making sure we can make sure to know name to symbol, symbol to name. Like potassium K, that gets a lot of people that they haven't had chemistry in a while, or sodium, as Na, things like that. So some of the ones that aren't super obvious maybe catch you off guard if you forget. Another thing important in chapter 1 is discussing the difference between like a chemical reaction versus a physical reaction. And sometimes it's made confusing when we do things like this. Like if I were to write like water solid and use like a chemical reaction, and we introduced chemical reactions in chapter 3, but if I write this as a reaction, I'm sure you've seen reactions written out, that this looks like a chemical reaction because you have some sort of reactant, some sort of product. But notice that the reactant and the product is the same substance, it's water. This is actually a physical reaction. So a phase change is an example of just a physical state of matter change. It's not really a change of form. So to have a chemical reaction, we want to change from some type of molecule into some other type of molecule. Now we'll learn as we go that you conserve matter, that you're not going to destroy elements in a chemical reaction, you just change what they're bonded to. So for a chemical reaction to occur, we have to have some sort of fundamental change in the atomic structure or the molecular structure of the substances. So this here would be a physical reaction. Even though it looks like it's written out as a chemical reaction. And an example of a chemical reaction, and obviously there are so many reactions that we can write, but one that I'll write for today is H2, so 2 hydrogen gaseous molecules reacting with an oxygen molecule. And I think the name molecule comes up in the next slide, but a molecule is just when we have 2 or more atoms connected together. It could be the same type, like 2 hydrogens, H2 is a molecule, O2 is a molecule. H2 is not an atom. H2 is comprised of 2 atoms, so it's sort of that idea. And these can react together to form 2 water molecules. Let's actually leave water, it doesn't matter so much. I'm going to write water as a gas. Okay, so let's actually do that chemical reaction. I actually intended to do this last time, but it kind of fits in here nicely. So we have inside this balloon, hydrogen and oxygen. What I'm going to do is do this chemical reaction. All I need to do is put a little bit of heat to it, and the reaction is going to take place. It's actually going to take place very quickly. We're going to need a couple of ears. We actually want to couple with the palms of our hand, not our fingers. We want to get a good top. You don't have to do this yet. So I'm going to turn the lights down so it kind of goes to the balloon. got to blow a balloon up in a pumpkin. It was cool, but so that was pretty fun. So chemical reaction is, sometimes you can't necessarily tell if it's flying. It's cool. But you can sort of see, like, we're not going to reconstruct that balloon. One nice artifact of a chemical reaction would be that you had things change you can't just easily put back together. Like if you had water, melt, and you could refreeze it. You can kind of easily go back and forth on a physical change, a little harder to do, not impossible, but harder to do on a chemical reaction. Okay, so one other set of terms on this slide are intensive versus extensive properties. This is just getting at which properties are characteristic of a substance, characteristic of its properties, and which are just characteristic of how much of the substance you have. The characteristic term is intensive. So this one here is our characteristic property. Let me give a few examples so you see what I mean. Like a boiling point, a melting point, a density. So the boiling point of water is 100 degrees C at standard atmospheric pressure, no matter how much water you have. If you have a drop of water, if you have a gallon of water, a lake of water, the boiling point's the same. The same thing with the melting point. Same thing with the density. The mass per unit volume doesn't depend on how much you have. It's still about a gram per milliliter. Now, an extensive property is one that just is a quantity dependent. Quantity dependent property. So it's just reflective of how much of the substance you have. So like mass. You can have a gram of water. You can have 10 grams of water. You can have however many mass, what mass of water you wish. How much water you have is an extensive property. So some examples would be the mass of water, the volume of water, but not the mass to volume ratio. Like yes, if you have a gram of water, you have about a milliliter of water. But you can also have 10 milliliters of water, which would be 10 grams of water. You see the amount that you have depends on how much of the quantity you have. Like if you have a milliliter of water, 10 mils of water, the boiling point's still 100 degrees C. So the intensive property is the same, independent of how much you have. That's independent is where intensive comes from. And so then the dependent quantity, extensive, just depends on the quantity of the substance that you happen to contain. Now this is really, I think, just meant to show that different substances have different intensive properties. They have different characteristic properties. So if you have ethanol, if you have isopropanol, if you have sugar, they all have their own melting points, boiling points, densities, etc. that characterize the substance. On this slide here, I didn't talk too much. A compound here was just two or more elements bonded together. So let me make sure I mention that here, that a compound has to have two or more elements. Bonded together. So it just helps us understand that things like O2 is a molecule but not a compound because O2 only has one element present. But then okay, so this slide here helps us understand a couple other terms. So like when we picture an atom, like I mentioned, I'm just kind of picturing a single distinct kind of form of matter, so just one single ball, if you will, representative of some element. There can be lots of different things that might exist as an element. The most common things that exist as elements as gases are the noble gases. So this could be something like helium. Like if I'm thinking of a helium gas mixture, the noble gases exist as monoatomic gases at room temperature. And so if I'm thinking like a neon sample, it would just be a single ball of whatever it is that makes neon floating around in the container. Now, the air we breathe in is comprised mostly of oxygen and nitrogen, and those exist as molecules. Those happen to exist as diatomic molecules. So things like O2 or N2 are molecules, and they're also elements. So the elemental form, the most stable elemental form of oxygen is O2. The most stable elemental form of nitrogen is N2, and that's on Earth. So like in our atmosphere, at standard atmospheric pressure and temperature, those are the most common states of oxygen and nitrogen. So they exist as molecules. So anytime you have two or more atoms, even of the same element bonded together, we call that a molecule. And so then you can also have molecules though where you mix in a different element. And there's many different examples. You can think, water is one of them. Ammonia is another. This one kind of looks like ammonia, so I'll use that as my example because I have 3 things bonded to a third. So anytime you have 2 different elements present in sort of a thing that exists, things like water. So 2 hydrogens onto 1 oxygen, we call that a molecule, but of a compound. So I think compound would look at something like NH3. We could say this is a molecule, but also a compound. And these are molecules, but not compounds. And then obviously things like helium, monoatomic gases, just atoms, are neither molecules or compounds. Now, one thing that's a little confusing is when you start talking about compounds like ionic salts, like sodium chloride and sodium nitrate, things like that. So if you have something like NaCl, this here is definitely a compound because we have 2 elements present. So this is a compound. But we're going to see later that it happens to be an ionic compound, and that ionic compounds have some interesting properties. We don't need to dwell on those so much here today, but it's not really a molecule. And if you get confused by that, you're not sure what that is, when we get to chapter 4 and we start talking about electrolytes and how ionic compounds behave, this might make a little bit more sense. But this is actually something we generally think of as being not a molecule, or it doesn't exist as like a molecular compound, it exists as an ionic compound. The real difference is when you have water or a molecular compound that's, say, a liquid, you would have a water molecule adjacent to each other, but each of the water molecules being separate. If you have a chunk of sodium chloride salt, you have a bunch of plus, minus, plus, minus, plus, minus. You don't have just 2 units of sodium chloride, another 2 units of sodium chloride. They all link together. And so they all pair up into more of an extended structure. And so that's why we tend to think of sodium chloride not really behaving molecularly, but this is why ionic solids have a lot of different properties. But that's not really the point of this example right now. But it's just I wanted you to kind of see the way I look at ionic compounds a little differently. And if you can't recognize ionic compounds just yet, we actually name them in the next chapter, and we'll go through how to recognize them a little bit better as we proceed. Then we can also have mixtures. So you can have mixtures of things. And this isn't an extensive list of mixtures. There's all different kinds of mixtures you can have. You can mix molecules, you can mix atoms and molecules, you can have gaseous mixtures, you can have liquid mixtures, solid mixtures. And this is just an example showing that you can have all different kinds of things mixed together. And so this is just showing us one different type of a mixture that happens to have molecular compounds, molecules, and an atomic gas mixed together. But again, you can have anything you wish mixed together in the form of a mixture. So for most molecular compounds, you can undergo the transitions from gas to liquid to solid. Now, the reason why I say most is if you picture, sucrose or something. I'm sure some of you guys have had sucrose and butter on the stove, and you're sort of melting the sugar. Maybe you did this in the form of brown sugar too. But it caramelizes, and it doesn't really melt in the normal way that most compounds melt. So the sugars are actually breaking down and decomposing as they melt. So not every molecular compound is going to undergo the perfect transformation from gas to liquid to solid. Some solids, if you heat them up, are going to start decomposing and changing and actually undergoing chemical reactions. But something like water is a good example where we can think of it as going from the solid form where we have a more ordered arrangement of the molecules, but still distinctly separate molecules. Water in the ice form still has distinct H2O molecules where think of the hydrogen and the oxygen that are bonded together. Those are still closer together than the adjacent oxygen in some other water molecule is to that hydrogen. Whereas if you had sodium chloride would be repeating with a very regular bond length for all those atoms in the structure. Just to give us a sense of a difference between what it means to be solid in the form of ice. If you can imagine having oxygen, 2 hydrogens attached, those same 2 hydrogens remain attached to water if you melt it too. So they stay together, so those oxygens and 2 hydrogens stay connected together as we undergo melting in the liquid water. And then as the molecules separate, that's the vapor phase. So the vapor phase is where the molecules can break their attraction for each other and then go into the gaseous state. We get into a discussion of states of matter, like the final 3 chapters we cover, chapters 10, 11, 12, go through gases, liquids, and then solids, so we can understand some of their different properties. And so this slide here is like one in the textbook that's slightly confusing because you can't always undergo this flow chart. Like if I just handed you a substance, you couldn't necessarily answer every question without having some extra information. And it kind of makes it seem like you probably could do that. But most of these questions that are asked, sometimes you can answer them just by looking. Sometimes you have to have more information. But this is just to get us into thinking of how we can break apart sort of matter and maybe answer some questions. If we have some questions answered, we can understand if the matter is a mixture, if it's pure, just one substance, and if it is a pure substance, is it a compound? Is it a pure atom? Or excuse me, a pure element. And so matter, you have some piece of matter, you're not sure what it is. Let's say it's a clear liquid. So you get handed a clear liquid. Can you see if it's uniform throughout? That means when I'm looking at the clear liquid, do I see like 2 phases? Do I see like an oil and water type phase? Or do I see one single phase where it appears to be uniform? That question you can usually ask by inspection. You can usually look at something and see, is the whole thing the same? If I look everywhere, does it look the same? And if it does look the same, then we just say that it's homogeneous. Now, it doesn't mean it's a homogeneous mixture. We just mean it looks the same by homogeneous. Now, separate that from the other word, heterogeneous. If something appears heterogeneous, then it like has 2 phases. Like if you can see multiple different phases, if you can tell that there's 2 different colors within like a solid, you can imagine, well, something's making up the one color, something's making the other color, or something's making up the one phase, a different substance is making up the other phase. So I know if it's heterogeneous, it has to be a mixture. So if it's heterogeneous, you definitely have a mixture. Okay, and so then if it's homogeneous, you're trying to figure out, is it homogeneous mixture or homogeneous pure substance? And now this is the question that you have a really hard time just by looking at something. Like I could obviously have mixed up like sugar water, and I obviously could just have water. And both of them would look like clear liquids. And you would have no way of telling which one was which just by simply looking at the water. But if I were to tell you, well, I added water to this one, or excuse me, I added sugar to this cup of water, it stirred it up, and it dissolved, then you would know that that has a variable composition. Now, a variable composition means if we could have, I sometimes call it molecular goggles. If I had molecular goggles, a variable composition would be, oh, I see water molecules here, I see sucrose molecules here, I know I have a mixture. So a variable composition just means that you can see somehow, either through knowing from the preparation of the mixture or from maybe some sort of test that you do, that there's more than one substance present within that substance. So variable composition just means there's 2 or more things that you can see with some help, either with the help of knowing how the mixture was prepared or some sort of experiment that shows you the composition of the matter. So a variable composition means there's 2 or more things present, and then it looks uniform. If it looks uniform, 2 or more substances, then that's a homogeneous mixture. So a homogeneous mixture is just 1, 2 or more substances like perfectly mixed together, and then we can see with our eyes that it appears to be perfectly mixed. And then if we know that it does not have a variable composition, so we look with our molecular goggles, or we know that we just put one pure thing into a container, then we know that we have a pure substance. Now, when I say substance, I mean one pure compound, one pure molecule, one pure atomic element sample. It's just pure for whatever it is, with nothing else present, so one single substance. Now we should say, most of the time, nothing's ever truly pure. So when I say I have pure water, it's probably like 99.9% water. There's always going to be some impurities even when something is quote unquote pure. So you have to imagine that, when we say something's pure, that it's within the limits of the preparation of the sample, that nothing intentionally is mixed together with the sample other than maybe some small impurities. And so then if it's a pure substance, the question is, does it contain 1 or more different kind of atom? Sometimes, you can say, I took a sample and I put a high voltage electricity on it and I saw 2 different things emerge. And so like if you do this to sodium chloride, you can see the sodium forming and the chlorine gas kind of separating off of it. And so that kind of shows you that sodium chloride has to be some sort of compound to have the separation of the elements into their different states. And so does it contain more than one kind of atom? If so, it's a compound. And if not, then you have a pure elemental sample. So like you took you take a pure sample of copper. You don't know it's pure copper, but it looks like copper. and then you try everything you can do to separate into different elemental samples if it were a compound, and it always stays the same, then it contains only one atom, and therefore is just simply elemental copper. Okay, and so let me give you just a minute or two to think about this with your neighbors or even just amongst yourself. How would we just describe a sample of table sugar? So which of these terms do you think applies? I'll give you like a minute to think about this. Okay, so let's take a look here. Now, I sometimes really don't like questions that say which of the following does not describe, because sometimes you start looking for the thing that does describe it and then you get confused. But so this is looking for a term that isn't sort of correct for the description of the sample. So maybe you have to know a little bit about table sugar, but really not too much. I mean, the only thing that's maybe useful to know about sugar is that it mostly contains sucrose, and sucrose is, it happens to have the formula, not that you need to know this, C12H22O11, and that, that ionic compound, that's going to be metal, non-metal. This isn't one of those ionic compounds. Like, this is a molecule for sure. Like, this is also a compound because we have more than one element present. So this is a molecular compound, meaning a compound comprised of elements. And so the sample would indeed contain molecules. The sample indeed contains a compound. Is the sample homogeneous? Yeah, like this question is, I think this word's a little tricky here because it's not saying it's a homogeneous mixture, it's just saying it's homogeneous. It appears homogeneous. Like you have table sugar, it just looks like white crystals throughout, very uniform in appearance, so it's homogeneous. And if it looked different, if we had like mixed together like pepper and sugar or something, you can clearly see that there's something else present. You would know that it would have a variable composition, it would be a heterogeneous mixture. So it's not a heterogeneous mixture. And so terms A through C apply. The reason why I didn't say it's a homogeneous pure substance or homogeneous mixture in this problem is because I think it's hard to know if, like from your vantage point, if sucrose contains one or two sugars, is it a mixture, what kind of impurities might be present that we really don't know about. It really turns out to be 99.9% sucrose of that one formula, but I don't think most students would necessarily know that. So I think, though, we can definitely know that it's homogeneous throughout. That's that problem there. And maybe we'll just do this problem here together. Which substance below is best described as a pure element? It's kind of funny. I used the lead in a lead pencil as an example because it's really not lead. It'd be kind of, I think, weird if we put actual lead into a pencil. Most of you guys probably know what's in a normal pencil. What's in a normal pencil? Graphite. And then I can imagine not knowing graphite is a form of carbon. Yeah, so graphite is really just one of the elemental forms of carbon. Carbon's really fascinating, probably the most fascinating element. I don't know, maybe that's debatable. But carbon has graphite as one of its common forms, but also diamond. It's kind of funny that the one form we just write with and throw away and don't think too much about, and then the other form is very precious and we collect and sell for a lot of money. And so it turns out that the lead in a pencil is mostly carbon in the form of graphite. And that, of course, would be a pure element. Obviously, coffee is not a pure element. Coffee has water, has a molecule and a compound and other different flavor stuff present, so coffee is not a pure element. What about air? Air is comprised of elements, but not just one pure element. So we have, obviously, mostly nitrogen is about 78% of air. O2 is about 21%. Does anybody happen to know what the next most abundant substance is in the air we breathe? It's actually argon, is about 1%. I have no idea why, it just is. So argon's about 1%. Then you think about like water vapor is a high component. Unfortunately, CO2 as well and some other substances. An ice cube obviously is a compound. And so these ones aren't, so it's obviously just the lead pencil is the example of the pure element. Okay, and so let's get into just a short discussion on how we could separate mixtures. And so one of the things that's kind of interesting is if you have a mixture that's homogeneous, it's going to be hard to separate the substances. But if you have a heterogeneous mixture, it could be easier. Probably the easiest time to do a separation is if you have a solid liquid mixture. It's really easy just to imagine putting some filter paper in and then filtering off the solid from the liquid. This is also sometimes useful if you have, maybe you have some sort of compound, like that's maybe it's ionic, that's in water, and you can add something that would cause an ion of that compound to separate, to sort of precipitate out a solution. We do this in one of our experiments where you have like solutions of, you don't have to know this today, but it's like I think you have lead nitrate and potassium iodide, both of which are clear and don't have any solids present. Mix them together into solid forms and you can separate off the solid. So filtration's useful for doing a solid liquid separation. An interesting liquid-liquid separation is a distillation. This one here is useful when you have two what we might call volatile liquids, or maybe just one volatile liquid is really all you need. Something that if you heat up the mixture, one of the substances has like a lower boiling point and boils off faster than the other substance. They use the example of salt water, where if you distill like sodium chloride in water, the water predominantly boils off first, the salt's mostly left behind, and then you're collecting here mostly just the pure water, and then you're leaving behind your NaCl and other salts. I don't think this really works super well. You might think of distillations of alcohol, so if you have an alcohol mixture, alcohol has a lower boiling point. Actually, I think that's in the next question, but if a substance has a lower boiling point, when you boil the mixture, that lower boiling point substance will be more in the vapor, and you can collect that higher concentration of the vapors in your collecting flask. Flask obviously is the one that we're collecting, and the other, so like I said, I think, yeah, that's this question here. So if you have a mixture that's say 15% by volume, I think that's, when you ferment something like grain or something to get alcohol, you're going to get maybe 15% or so is the highest concentration of alcohol you're going to get. So if you want to make whiskey or vodka or things like that, not that you guys are interested in that, but if somebody else wanted to make that sort of substance, what they would probably do is think, well, let's do a distillation. Now, the water boils, of course, at 100 degrees C, the ethanol, though, at 78 degrees C. So that's the big difference, is whenever you have two liquids present in a mixture, and one of them has a lower boiling point, or just if they differ in boiling point, the lower boiling point substance can be collected, but the question is, where are you going to collect that liquid? So if you're doing a distillation, which statement best describes the liquid in the receiving flask? And so the receiving flask is the one that we're heating. So give this a minute and think about the best answer. Okay, so what do we think here? Does anybody think it's pure ethanol? Does anybody think it's pure ethanol? It gets close to pure ethanol, just not quite there. So I think the better answer is going to be the receiving flask ends up containing more ethanol. So the concentration of the ethanol in the receiving flask is simply going to be greater than what we begin with, but not necessarily pure. And then the flask we started with is going to end up having, less. So the flask we started with will end up having a lower alcohol percentage. Now you may wonder, why is it that it doesn't come out as pure? Maybe that first drop is close to pure, but still not pure. Does anybody know the highest purity of alcohol you can get to by distillation? Does anybody happen to know? It's like 95%. It's kind of a question. Is anybody from Kentucky in this room? It's like moonshine. The best you're going to get to is 95%. And you may wonder, well, why is that? Well, the reason why is because if you boil 95% ethanol in water, the vapors have that exact same composition. And so the vapor ends up having the same composition. That's called an azeotrope. You don't have to know that word now. But it's something that liquids, whenever they distill, will eventually form what you call an azeotrope, the point at which the vapors end up having the exact same composition as the alcohol. There's probably a gory math problem like chapter 13, or I think it's chapter 13, you do in Chem 1220, where you actually can work out what the composition should be in the vapor phase versus the starting sort of flask that you're distilling. And for ethanol and water, it ends up at 95%. So if you want to get to 100% alcohol, you have to add some sort of drying agent. Yes? So the first part of the, I'm not entirely sure why that might be the case. It could be that there's other impurities, like the methanol boiling off would be my guess. So probably the little bit of methanol that's in alcohol are going to be really highly concentrated in that first drops. And methanol is, of course, more poisonous than ethanol. Sometimes I hear people say methanol is poisonous, ethanol isn't poisonous. I'm like, well, it's kind of a dose. You could just drink less methanol than you can ethanol, because ethanol is still a poison. It's just you can withstand some of it. And interestingly, if you do drink methanol, the treatment is actually drinking ethanol, because it's like a competitive inhibitor. That's more of a biology topic. But I think that's probably why. There's probably other things in the first drop that aren't either alcohol, the ethanol that you were looking for, that are more toxic. Yeah. Okay. Awesome. Yeah, I literally just made up the answer too, so I'm glad that my intuition worked out. Okay, and so then the other form of separations, and this is, I just bring this up because it's in the book, and it's maybe not the most intuitive form of separation. We don't really ever talk about this other than on this one slide here in this class. Maybe you might see it in one or two practice problems later, but usually it's not even too represented in practice problems. But it's a form of chromatography. I really bring it up here because this is a really common separation technique that we use in organic chemistry. You'll do this if you take the OChem lab course 25, 40, and 50, which if most of you guys are pre-med and pre-something, or a bio major, you're going to end up taking that lab class. Now, the way chromatography works is it's kind of a separation where you have your liquid mixture, where you have two components you're trying to separate, and you're going to flow those compounds in that liquid mixture through a solid support. So you have something like silica gel, something like alumina, just something that's solid that has like little arms on it that hold on to molecules as molecules flow by. So imagine your molecule floating through silica gel. If you have an attraction with that solid support, it's going to take you longer to make your way down the column. You're going to stick. And then if you don't have the same attraction with that silica gel, you're going to flow through more quickly. So the mixture kind of starts to go like this, where the one compound just goes down the column faster, and you can begin to get a separation of the components in a mixture if they have different, what you call, rates of absorption onto that solid support. This actually is the pen ink on paper problem. If you get some water onto like a sheet of paper, like so black ink on paper, you can see that it's like purple and blue ink dyes if you've seen them separate on paper. And the reason why you can see them separate is because the paper is like your solid support. So the paper is the solid, and then the ink dyes have different colors, which just happen to travel at different rates through the paper. And so that's how you can start to see the emergence of different inks that are together on like a blot that gets wet and ends up separating. So that really is an example of chromatography that you're seeing when you see like that ink blot kind of deal. And so now this only works, like I mentioned, if you happen to know what the right type of solid support is, what the right type of solvent flow to mix through that allows these compounds to actually separate. So it's a hard to apply technique, But it's easy enough to, I think, understand that just the blue substance is sticking better. The green substance has like the lowest affinity with the solid support. That's why it's making it through the column the fastest. Okay, so let's get into some topics that get into some different units and get into some math parts of the chapter. Let's talk a little bit about energy. And so energy is the capacity to do work or to transfer heat. So something that has, let me also mention real quick, these slides are on Carmen. And like this was mentioned last time, I don't know if you guys realized I was following along the same slide. So I just wanted to make an aside on the lecture slide page of Carmen. So a link right on the front page has a link to the lecture section, and then from there there's like these lecture slides. And I'll post those for each of the chapters as we go throughout the class. I just happened to notice a few people writing a lot, and I was thinking, oh, I hope you all know that these slides are available, so you don't have to write down all the words that are already on the slides. But anyways, nature of energy, the capacity to do work or to transfer energy. We talk more about heat in chapter 5, so this is just going to be a really quick sort of introduction to a few different units of energy and a few different ideas. But the sort of idea of doing work is like pushing an object and moving an object. So that's the capacity to do work. So work is the energy associated with putting objects into motion. So this is, objects into motion. So moving the car by the energy being released from the burning of gas or the electrical energy being released. Or the transfer of heat, which is obviously just something hot making something else that was cold warmer. So it's just the transfer of heat from sort of hot to cold. And so work, so I guess I already had written this down, is the energy transferred when force is exerted on an object, causing the displacement of the object. This isn't really a physics class, so we're not going to talk too much about examples of calculating work as some exertion of force over some distance traveled. But you might remember an equation from physics, or if you take physics, you'll see this equation. Work is force times distance, so it's the force you have to exert on an object to move it some distance. I'm not going to play around and do math problems with that equation, but I just, you may have seen that equation before. And that heat is the energy required to cause the increase of temperature of an object. And you may have seen this equation too, that Q is equal to mCs delta T. If you've never seen this before, we'll use this more and define it again in chapter 5, but this is just sort of the heat required to cause a certain mass of water to undergo some sort of temperature change. And then this is the specific heat. It's just an intensive property for a substance that relates to how much heat it requires to raise that object's temperature. Again, we're not giving the equation here to use it, but just an equation we'll see later, just to kind of plant a seed that we'll use in chapter 5 on relating heat changes and quantities of substance that are undergoing some temperature change. Then I'm sure we've all heard the words kinetic versus potential energy, and so kinetic energy is the energy of motion. So objects in motion have kinetic energy. So we usually think of this as 1/2 mv squared. These are kinetic energy. So objects in motion have a kinetic energy. This is a function of their mass and their velocity. Again, not giving, most of these equations, we will use the kinetic energy equation in an example in a minute. But for the most part, just kind of getting an introduction to some different equations that relate sort of these ideas of work, heat, energy. Potential energy is really, I think, harder to give an equation for this. This is just object top of the hill, so it has a lot of potential energy that it can release into the form of kinetic energy if you were to nudge it down the hill. Now, where potential energy kind of moves into the molecular example, so it's easier maybe to understand the physical examples of the ball on the top of the hill, the bicyclist going down the hill, an object in motion like a car. But think about how this relates to chemistry. So think about our hydrogen-oxygen balloon. Before I blew it up, would you say that it had a lot of potential energy? It did, because it had a lot of energy stored into those bonds that could be released as we formed water. So hydrogen and oxygen were actually symbolic of the ball at the top of the hill. They're just waiting to be nudged to go down the hill. As soon as we gave it that spark, it happened to be that one reaction was very fast, and then as soon as we started, the reaction just went by a chain, kaboom, and went. And so in a way, that was an example of a chemical reaction releasing kinetic energy from the stored potential energy. Now you may say, well, how did you store the potential energy? well, we stored it by somehow taking hydrogen, which isn't readily available, and creating it. So energy went into creating the hydrogen, so that was the energy that was stored in the form of hydrogen that was then released through the reaction. And so the physical examples, bicyclist top of the hill, has a lot of potential energy that can be released into the form of the motion energy, 1/2 mv squared, and the kinetic energy as we're gaining velocity going down the hill. And the same thing here with that balloon that we blew up, that we were releasing energy that was stored into the bonds of those molecules as they were reforming new bonds. Now, terminology is just being said here to understand later where we'll have some equations and more thought put into this. But think about how we started with something less stable and ended up with something more stable. That might be like a thought you had for the water. We formed more stable water, and you know that because it went kaboom, like you saw it with your eyes. Now, maybe you didn't see with your eyes that hydrogen and oxygen went into the balloon, but trust me, H2 and O2 really went into the balloon, and then we're making that stable water molecule as a result. And so our kinetic energy, energy of motion, the magnitude depends on the object's mass and velocity, as we mentioned. And the potential energy is an object. The potential energy of an object depends on its relative position compared to others. It kind of depends on the hydrogen being bonded with itself, not with an oxygen in between. Makes a big difference. Okay, so let's talk about the SI unit of energy. So the SI unit of energy is the joule. And so the joule is defined, 1 joule is 1 kilogram meter squared per second squared. And so the, I don't know why that 1/2 appeared. There shouldn't be a half here. So like, it should just be a 1. A extraneous half appeared. So 1 joule is 1 kilogram meter squared per second squared, or meter per second squared. And so you kind of see how the base unit of the joule is coming from the unit of mass being in kilograms and the velocity being in meters per second. And then we're squaring that. So the units for joule really come out naturally from just thinking the equation for kinetic energy, mv squared, SI unit of mass is the kilogram. We'll see that in a minute. But the SI unit of mass is the kilogram, distance meter times seconds, and so it just kind of falls out naturally that the SI unit of energy is going to embed those fundamental SI units of kilogram, meters, and seconds. Okay, so we can actually solve a problem here. Let's work on this one here together. So we have a mole of oxygen, 32.00 grams. The word mole, we'll talk about that in chapter 3, so if you don't recognize the word, don't worry about it. We're just being told here that that's 32 grams. This is getting at a mole of O2. So if you remember the molar mass of oxygen in 16, we talk about atomic weights into chapter 2, into chapter 3. So we're just using the mass here. We're having it given to us, but it's coming from 16 times 2 grams per mole. But it's in a container at room temperature. The average velocity of the particles is 1,080 miles per hour. What is the kinetic energy of the particles in kilojoules? So right off the bat, we actually have to do that transfer of units thing, right? If we're going to want to solve for the kinetic energy in this unit of joules, we even see the kilojoule. So we start to we can break this down into some things we can already know from some prefixes and some conversion factors that we ought to be able to remember. Like a kilojoule is 1,000 joules. That's what the kilo means. A kilo is like that 10 to the 3 kind of conversion factor. So our kilojoule is 1,000 joules. So that kind of relates kilojoule to joule. Then we can remember, well, that would be 1,000 kilograms meter squared per second squared is the conversion of a kilojoule into that fundamental SI unit of kilograms meter squared per second squared. So if I want to calculate the kinetic energy using my equation 1/2 mv squared, so 1/2 the mass, we have 32 grams in kilograms. So kilograms 1,000 grams, right? Let's actually write that out. So instead of converting it right off the bat, let me write 32.00 grams. And then just use the conversion, 1,000 grams per kilogram. And our gram cancels. So this is dimensional analysis. We'll use this a bunch in the class. We eventually get to dimensional analysis. We've all seen it before. We don't need to wait to the dimensional analysis section to plug in and use dimensional analysis. So that gets us towards the unit we want for our kilojoules of kilograms. But then when I want to plug the velocity in, I want to plug this in meters per second. And I could probably do the conversion all in one step here in the problem, but I'm going to do the conversion from miles per hour to meters per second separately down here. So if I have 1,080 miles per hour, let's just go through the dimensional analysis. Now, you get non-SI unit conversions. So like in a problem on a test, I would have somewhere on it that, 1 mile is 5,280 feet. Not everybody, if you come from another country, you're probably like, what the hell's a mile? Mile is kind of like a kilometer, but not quite. And so 5,280 feet, 1 foot is 12 inches. 1 inch is 2.54 centimeters. So these would generally all be given if you need them on a test. Now, one last one that generally wouldn't be given just because it involves the centi unit. So how many centimeters in a meter? I already started writing it, 100 centimeters in a meter. Okay, and so we can use those to help us go from miles into meters per second. So we might use the 1 mile is 5,280 feet. We have 1 foot, 12 inches. 1 inch is 2.54 centimeters. .100 centimeters is 1 meter. So if we stop here, we've gone from miles to feet, feet to inches, inches to centimeters, centimeters to meters. If I stop the calculation right now, I'd have the meters per hour. We just got to go meters per second. And so 1 hour obviously is 60 minutes. And then a minute's obviously 60 seconds. So let's do that. So we got 1,080 times 5,280 times 12 times 2.54. Divide by 100, divide by 3,600. Then is it working out to 482 meters per second. Now you may say, how many of you guys are thinking, why don't you just use a solver? How many of you guys are like, just Google it? Well, I wanted to know how to do the conversion. I want us to practice doing dimensional analysis because it's really not that hard. And so we plug in our 482 meters per second, and we have kilograms meters squared per second squared. So 482, it's actually 483, but so that works out to be about 3,700,000. But that's joules. So this works out to be in joules. I just need to divide this by 1,000 joules per kilojoule to go into kJs. Because kilograms meters squared per second squared is a joule. I just divide by 1,000. And I get 3,732 kilojoules. Oh, but I forgot to divide the mass by 1,000. All right, let's do this. We will begin class Monday with the actual result in the calculation, that final step, just to get that actual answer out correctly. But so, conversions, chapter 1, sig figs yet to come. So that's class for today. Have a great weekend, everybody. I'll see you here on Monday. We'll wrap this problem up on Monday.